Let's look again at our drawing of water. Oxygen holds its 6 valence electrons in 4 equally spaced hybrid sp3 orbitals, and hydrogen holds its 1 electron in its 1s orbital. Without saying so explicitly, we showed that the orbitals are bonding through their overlap. The hydrogen 1s orbital sits kind of couched inside of the oxygen 2sp3 orbital, and the 2 electrons complete each other's valence shells. In so doing, the electronic structure of both the hydrogen and the oxygen relax to a lower energy, and it would now take energy to pull the hydrogen away from the oxygen. In other words, we created a bond. This orbital overlap to share electrons between incomplete valence shells is at the heart of valence bond theory. The increase of electronic density between the two nuclei also produce an area of negative charge that serves to decrease the repulsion between the two positively charged nuclei. A bond that forms on the line between the two nuclei is called a sigma bond. Because hydrogen only has the 1 electron, and that 1 electron is likely to find itself between the two positively charged nuclei, hydrogen always forms sigma bonds. Let's look at a second example. C2H4 ethene. Both carbon atoms are sp2 hybridized, and both are bonded to the 2 hydrogen atoms by sigma bonds. Something more interesting happens as the carbon atoms bond. When we place them close to each other, we can create a bond with the overlapping hybrid orbital directly between the two nuclei. This is a sigma bond. The only remaining hole in each carbon atom's valence shell is in their p orbitals. The orientation of the p orbitals can change because a single sigma bond acts like a single nail connecting 2 boards of wood. It can act like an axis of rotation. However, once the p orbitals align, now they are close enough that their electrons can bridge into the other atom's p orbital, creating a second bond. Because the electron density is not directly between the two nuclei, this is called a pi bond. And with this second bond, there is no more rotation around the carbon-carbon bond, and the hydrogens are held on a flat plane, agreeing with experimental findings. Something similar would happen with C2H2, or ethine. In this case, both the hydrogens and the carbon-carbon bond are held in sigma bonds, and now there are 2 sets of p orbitals that we can use to make 2 pi bonds, for 3 carbon-carbon bonds overall. Finally, we should see the same thing when we replace some bonding orbitals with lone pairs, like in oxygen gas. The double-bonded oxygens have the same hybridization as ethene, so their valence shells complete each other in exactly the same way. We just have lone pairs instead of bonds to hydrogens. But let me show you what happens when liquid oxygen is poured between 2 magnets. The liquid oxygen is held in place by the magnetic force. That is to say, the oxygen molecule is paramagnetic. But if all of the electrons in the oxygen molecule are paired, then how can it be paramagnetic? And if it is paramagnetic, as the experiment shows, then how can all the electrons be paired? Again, experimental evidence tells us that our theory must be incomplete. We'll look at a correction to that theory next time.